What I want to try and explain over the next 10 minutes or so is...
You're not having 10 minutes.
Oh, okay. Over the next few minutes or so, I'll start again. What I'd like to explain over the next few minutes or so is why some materials are transparent and others are completely opaque, why light can get through some materials, why light can't get through other materials. In particular, glass. What makes glass transparent? Why can light get through this? Yeah, I've found a number of interesting and disturbing websites, I guess. So I thought, given that I was doing the 60 symbols video and looking at why glass is transparent, I thought, well, let's just Google it and see what everybody else says. And type in, why is glass transparent into Google? And you get a number of sites which just give you completely incorrect answers, completely wrong answers. Disturbingly wrong, in that they explain it in terms of, well, glass is like a liquid, and the molecules don't pack as tightly as they do in a solid, and therefore there are gaps in glass that the light can get through. That is wrong, badly wrong on so many different levels. Yeah, so what is going on is with glass compared to other materials, the important thing is how the atoms are arranged in the solid. And how the atoms are arranged dictates, and this is the really important bit, how the electrons are arranged. And it's how those electrons stack up in different energy levels, or the energies of those electrons, that dictates whether light can get through. Right, so what I'm going to do now is I'm going to pretend to be a photon. I'm going to move through this room, and this room represents a substance, lots of atoms, electrons dotted around everywhere. So I'm moving through with a certain amount of energy. And my job as a photon is actually to take one of these electrons from its ground state, its lowest energy state, move it up and bring it up to a higher energy level. And when I do that, basically my job is done and I'm absorbed and I don't make it through the solid. So if it's brick, for example, this is what happens. The photon comes through, it takes an electron from the ground state, moves it to a higher energy level, is absorbed, doesn't make it through. The substance is opaque. For glass and other special materials which are transparent, instead of what happens is that the difference in energy between the ground state and the high energy level, which we call the energy gap, is much too large. And as a photon, I'm coming through, and what I need to do, or to be absorbed, what I need to do is actually take one of these electrons and bring it all the way up here to this excited energy level. But I don't have enough energy to do that. I simply can't get it up there. So therefore I'm not absorbed and I pass through the material, getting out the other side, and so the material then appears transparent. So the energy difference between the ground state and this level, the difference between those two we call an energy gap. And an electron can only either be here or here. It cannot exist in between. We cannot excite it there. So the photon gives up that energy and transfers it there, and then it's the photon basically is dead. So when it comes to glass and diamond and other transparent materials, that energy gap between the ground state and that excited level is so large that photons of visible light, photons with visible wavelengths, photons that we can see, have not got enough energy to actually get it from here all the way up there. Right, so now we're going to go down the lab and we're actually going to do an experiment, or look at an experiment that the second year of undergraduates do here, which is to look at how light is absorbed in these materials. We have a light source, we have something called a monochromator sometimes is how it's pronounced, and what that does is from the white light source, it selects out a particular wavelength of light, a particular colour of light, a particular energy of light. And so this, at the moment, is telling us that the wavelength of this light is roughly, I haven't done the calibration, so I'm assuming it's right, roughly 525 nanometers. And so I'm going from, at this point, high energy photons with this bluey green colour, up to low energy photons. So what we have here is a sample. Now this is sort of midway between what we've been talking. It's not quite completely opaque, it's not quite completely transparent. You can see it's coloured, it's orange. It's an example of something called a semiconductor. What's interesting about this semiconductor is that that energy gap falls in the visible range. It means that some photons of light in the visible have enough energy to excite those electrons, whereas others don't. And we can actually measure that transition from where the photons have enough energy to where they don't have enough energy, or alternatively where the photons get blocked because they have enough energy, compared to where they actually get transmitted the whole way through. So what I'm going to do now is here, if it's just the light, just so we could see it, I've put on the side of the box. that contains the photodiode. This is actually the active part. So what I'm going to do here, so I'm going to move this across and put it on the photodiode. And now we see light getting through. What I'm going to do is put this sample in there. I'm going to put it in front of the photodiode. So the light is coming through from here, through here, through here, through here, going through the sample now and ending up on the photodiode. And you can see that we've got 0. And the reason we've got 0 light coming through now is that all the photons are absorbed, because photons of this energy have enough energy to promote electrons, to excite electrons across that gap, so they're absorbed, so they don't get through. When we change the energy, so we're going from the blue to the red, the dial will start to come up, because at that point the light is now getting through, because at this point the photons no longer have enough energy to actually get through the sample, because they're not promoting those electrons from the ground state to the excited level.